A warm welcome to this session in which I am going to have my teaching associate Sushrut Thakar participate. I told you in one of the earlier discussion sessions of this course that one of the things we want to do is to connect to you through our teaching associates, and Sushrut has very kindly agreed to do the needful today, to bring before me certain questions which he thinks a lot of students would have. And in fact, all of you should ask questions on the discussion forum, you should write what doubts you have, because then we can use them to frame and to plan these discussion sessions. We will look at a few other questions also in a discussion session. I am going to ask Sushrut now to tell me some of the questions and some of the points that he has identified, which could be weak links in the video that we have recorded, or which could also be somewhat difficult for people to understand, or which require more explanation. So go ahead, Sushrut, tell me what you have noticed.
Thank you, sir. So we talked about causality and stability in the lectures. So I thought that causal and stable systems are very important. But are there systems which are non-causal or not unstable, which are also used in real life?
That's very interesting, it's a very good question. So let's take them one by one. Now, what does causality really mean? In fact, let me repeat probably some of the things that I have said in the session. Causal means obeying the cause-effect relationship. Now, this cause-effect relationship is only meaningful in time, not in space, for example. So, you see, what I am saying is that it does not make sense to say something coming from behind is a cause, or something coming from the front is a cause. You see, I mean, somebody could push you from behind or somebody could push you from the front. Both of them are equally troublesome. So, in space there is no causality in that sense, but in time there is causality. Till now we have not really had any meaningful ways of going back in time. So, what it really means is that in time there is a clear sequencing in one direction. If you are dealing with real time implementations, you can only deal with past samples and the present, or past inputs and the present input. You can't really deal with future inputs or future parts of the input. So, in that sense, at a philosophical level, causality has a meaning in time, and that too when one wants to implement real time. If one wants to store data and implement things offline, then of course causality is not so important. In space, causality does not have much of a meaning. You could go backwards or forwards. In fact, if you look at images, you could do one dimensional processing on each of the rows of the image or each of the columns of the image. So, essentially, if I want to do two dimensional processing, when we deal with two dimensional signals, what we do is to process one dimensionally on each of the rows and then process similarly one dimensionally on each of the columns. That is one way to do two dimensional processing. Now, there again, upwards or downwards or left or right is symmetric. There is really no causality there in that sense. So, in space there is no causality. Now, coming to stability, you see, let me give you two examples of systems which are by design unstable. In fact, if they become stable, then there is nothing left in them. So, let us see two useful examples of unstable systems. The first is a discrete system, a bank account. Now, let us assume that the bank makes a calculation of the current balance in the account every once in so much of time. Now, you see, we will assume that time is fixed. So, maybe somebody I remember on the forum raised the issue of months have different lengths. Well, let us ignore all those differences for the moment. Let us say there is a fixed time interval after which the bank makes a calculation or recalculates what is the current remnant in the account and so on, it could including what you have deposited, what you have withdrawn, and the interest calculation all together, right. Now, suppose you operate the bank in the following way, your account in the following way. You deposit something in that account and just keep it there, do nothing about it. So, it is like giving an impulse input, or it is like giving an input. If it's so, you see, you could think now from the point of view of the bank, when it makes a calculation, it looks at all the transactions in a certain interval of time together for the purpose of interest calculation, for example. You don't keep calculating interest by the day or something. You look at a lump calculation over this period, all these transactions have taken place, this was the balance at that point in time, you make an interest calculation. No bank sits and calculates interest for every hour or every day or something. It's not a continuous time function in that sense. So here, let's look at the situation. So you put in some money into your account at one point in time. So it's an input which is non-zero at a particular point in time, and it's 0 else. So let's write down the discrete system. So you have x, let us say, without any loss of generality, x of 0 is a one-time deposit. Now, what kind of an output would you like in your bank account? You see, would you like that deposit to just remain as it is forever? Would you like that money that you have deposited to grow, albeit slowly? Or worse, would you like that deposit to diminish in time? So what would you like, Sushruth?
I would of course like the money to grow.
Yes, you want the money, if you have put in 100 units of currency today, you would like after maybe 1 year that it becomes 102 units, let us say, whatever be the bank interest rate, and then maybe after that it will be 102 by 100 times 102. So, each year you would like it to grow, compound, isn't it? Typically the interest compounds. So, you would at least, nowadays I think most banks operate on that principle of compounding the balance every so much of time. So, you would of course like it to grow, that is what your bank account would normally do. In fact, you need to do that to take care of inflation, you see. Now, look at it from the point of view of discrete systems. What are we saying when we say your account, your bank balance grows in time? What are we saying about its impulse response? You see, what is an impulse in this context? That impulse would be a one-time deposit. So, this x of 0 where you have fed in something at one time is like an impulse. So, it is like x of 0 times delta n. This is the input applied, an impulse input, and the output to this impulse is an exponentially growing sequence as a function of n. This is the impulse response after all, isn't it? Let's call it h of n. Now, how would you test for the stability of the system? The stability would require to check, you studied this in this week, haven't you? The stability would require you to check summation n mod Hn, and you will agree with me that this diverges. So, the system is unstable by creation, and that is what you want it to be. See, even if the balance remains constant, even so the system would be unstable. And what you would definitely not like is a stable system here. If the balance diminishes in time, you would not put your money in that account, definitely, isn't it? So, there are situations where a stable system is not desirable, like this one. Now, let me take another example from continuous time. You see, we have something called an oscillator in continuous time. An oscillator generates a periodic waveform with a small disturbance input. So, I could of course describe the circuit of an oscillator, but that would be beyond the scope of this course. But you could think of a very simple oscillator constructed out of inductances and capacitances. So, inductance and capacitance, when they cancel out one another's impedance, they could give you an oscillation. Now, what does an oscillator basically do? An oscillator generates a periodic pattern. Could very often, if it is a linear oscillator, it would generate a sinusoid of a given frequency, and that would happen just on a slight perturbation. In fact, the idea of an impulse has this physical meaning. You just perturb the system slightly and it generates a sine wave all of its own. Now obviously, if on applying a small disturbance like what you might call a very narrow pulse which tends towards an impulse, and you get a sine wave, a steady sine wave as an output, obviously that could be looked upon as the impulse response of the system, and that impulse response is not absolutely summable, it is so obvious. If it is a steady waveform, periodic waveform, it is definitely not stable. But an oscillator is very useful in communication systems, in many electronic systems where you want to keep time, or you want a periodic waveform to mark something out for you, or you might want a periodic waveform to be applied to the display channel, or there are so many reasons why you might want to generate a periodic waveform. So that is another example where unstable systems are what you want. If the oscillator was stable, it would not retain its periodic waveform at all, so it would not. So there are situations by themselves we must understand the properties, and one must not also put judgments on the properties immediately. So being causal is often the case in time, but non-causal systems have a place. Being stable is often what a system is designed to be, but then there are examples of unstable systems which are very useful. Very good. So let me have some more questions from you now.
Sir, we also talked about the associativity and commutativity of systems, LSI systems specifically, and I thought these are very basic properties of systems.
Yes.
So, are there any physical implications, or are they physically useful?
Very good. That is a good question. See, let us understand the meaning of associativity and commutativity at a slightly deeper level. So, let us take commutativity first. Commutativity essentially means interchangeability of order. Now, it is remarkable that only linear shift invariant systems guarantee commutativity. So, if you have two systems connected one after the other applying onto an input, you are not guaranteed that if you interchange their order, the output would behave in the same way. But if the systems are individually linear and shift invariant, yes, you are. Now, why is this important? Because in certain circumstances, with the inaccuracies that are there in linear shift invariant systems, it might be better to have one of them precede the other. So, if you have it could very well happen, for example, that you might have a system which is unstable and you have another system which is stable. Now, for whatever reasons, you have a choice of putting the stable system first or the unstable system first, right? You could put the stable system first and the unstable system next, or you could put the unstable system first and the stable system next, and both of them could be linear and shift invariant. It is always a moot question which is better from an implementational point of view. One of these configurations may have a merit over the other, and of course, when one goes into specific systems, one realizes this. Now, this can also, this, for example, you may have this choice in a slightly different sense. I have already told you about abstractions, so you have an abstract model of two systems, what they want to do to the input, but their realization could be in different forms. So, you could realize one of them as a mechanical system and the other one as an electrical system. Now, you might very well have a situation where you have full freedom which part you want to realize in mechanical form and which part you want to realize in electrical form, and if both of them are linear and shift invariant. So, if putting the if you know that putting the second system first will allow you to realize it more easily in a mechanical form, and that is the form in which you want to do the first operation, then that freedom is available to you. The abstraction is the same. So, the interchangeability is the abstraction level also. It may be true that the first system is more convenient to realize in mechanical form and the second system is more convenient to realize in electrical form. So, let me give you an example. You want to do something related to the kind of force viscous system, that we talked about that. So, you want to study some kind of a force, acting upon a mass with a viscous context and all that, viscous friction and whatever. So, you want to study that context. Now, you also want to do some operations on the output that you get. So, you record the movement and then you want to convert that movement into an electrical form, and you want to do some filtering on the electrical form to get some kind of a pattern. Now here you could in principle do the reverse. So, you could think of a filter which works in the mechanical domain, but that is not so convenient to do. You might want to implement that mass force system in the mechanical domain and then implement the filtering operation in the electrical domain. So of course you could do it the other way, but then it's not. So the order in which you place a system may have some other physical context of choice. So at the abstraction level, commutativity means that I could interchange the order to my convenience, right. So yes, Sushruth, we will see some more questions after a couple of minutes. Yes, so we will continue. Yes, and associativity too. Yes, I need to talk about associativity. So let's break for a couple of minutes and we will then resume.
Okay, sir. Thank you.